The Avalanche Consensus Whitepaper presents a new way for blockchains to reach agreement without relying on proof of work or classical Byzantine fault tolerance. Instead of linear block production or leader election, it introduces a probabilistic model built on repeated random sampling. This approach achieves fast finality, high security, and true decentralization while consuming minimal energy. In Avalanche, nodes don't need to communicate with the entire network. Each validator repeatedly queries a small random subset of peers to determine their preference for a transaction. If most responses agree, the node adopts that choice. As this process repeats, the system rapidly converges on a shared decision. This behavior is called metastable consensus. Once the network leans strongly in one direction, it becomes increasingly unlikely to change. The white paper defines three related protocols: Snowflake, Snowball, and Avalanche. Snowflake introduces random peer sampling and finalization after several consecutive confirmations. Snowball adds counters that accumulate confidence with each round. Avalanche extends these ideas to a directed acyclic graph, or DAG, where multiple transactions are processed in parallel rather than one block at a time. This parallelism removes bottlenecks and greatly increases throughput. Traditional consensus mechanisms rely on leaders or sequential block creation. Avalanche eliminates both. Every validator participates equally, continuously sampling peers and updating its local state. The result is a decentralized system capable of thousands of transactions per second with finality in under 2 seconds. Because validators act independently and asynchronously, decisions are finalized without waiting for global synchronization. Despite its simplicity, the system is secure. Avalanche can tolerate up to 1/3 of validators acting maliciously without losing correctness. Random sampling makes coordinated attacks extremely difficult, and the absence of miners or block proposers removes common attack points found in other protocols. Instead of deterministic voting rounds, Avalanche relies on probability, making manipulation statistically improbable even under hostile conditions. Scalability is another core feature. In most blockchains, communication costs increase as more validators join. Avalanche maintains constant overhead because each validator interacts with only a small, fixed sample of peers. This allows network capacity to grow with participation rather than slow down. The system's performance remains stable even as it scales to thousands of nodes, proving that decentralization and efficiency can coexist. The consensus mechanism is also energy efficient. Validators don't mine or compete computationally. They perform lightweight queries and cryptographic signatures, consuming minimal resources while maintaining strong security. This efficiency allows Avalanche to support global participation without the environmental costs of proof-of-work mining. The protocol is resilient to latency and connectivity issues. Because consensus is achieved statistically, temporary delays or local network partitions don't halt progress. Nodes resynchronize automatically as sampling continues, keeping the system stable even under real-world conditions. This flexibility makes Avalanche suitable for geographically distributed public networks as well as private or enterprise environments. Economic incentives reinforce security. Validators stake AVAX, the native token, to participate in consensus and earn rewards for accurate operation. Delegators can stake through validators to share those rewards. Since there is no competition for block production, rewards are distributed evenly, reducing centralization pressure and encouraging long-term participation. Avalanche Consensus bridges classical and Nakamoto-style systems. It combines the safety and finality of Byzantine fault tolerance with the openness and permissionless nature of proof-of-work. Transactions are confirmed within seconds and become irreversible once accepted by enough validators. This balance of speed, security, and accessibility makes Avalanche one of the most advanced consensus frameworks in use today. This protocol underpins the entire Avalanche ecosystem. Every subnet and chain relies on it to coordinate validators and secure assets. Parameters such as sample size, quorum thresholds, and staking limits can be tuned for different use cases. This flexibility allows Avalanche to serve everything from decentralized finance to gaming, tokenization, and institutional systems. The Avalanche Consensus Whitepaper represents a breakthrough in distributed systems. By using random sampling and probabilistic finality, it overcomes the long-standing trade-offs between scalability and decentralization. It shows that consensus can be fast, inclusive, and sustainable at global scale. Avalanche proves that distributed agreement can be efficient without hierarchy. It demonstrates that decentralization does not have to mean delay. For more insights on Avalanche, consensus design, and scalable blockchain innovation,